In the name of God. Hello, dear students. My name is Masood. I'm a physics teacher. We are in Ferho's website at your service to explain physics curriculum, grade 12. Our goal is to make the subject easy for you as much as possible. Let's dive in with the book. I'm gonna explain the contents of this book, especially chapter 1. I'm gonna explain the contents of chapter 1 for you. Chapter 1 talks about the rotational, and this is the title of chapter 1, rotational motion and the law of gravity, right? This chapter consists of 3 sections. Section 1.1, measuring rotational motion. Section 1.2, tangential and centripetal acceleration. Section 1.3, causes of circular motion. So they are, let's say, sections. There are sections for, let's say, chapter 1. Let's start with the section 1.1, measuring rotational motion, and the first subject is rotational quantity. What's the rotational quantity actually? Before I explain this one for you, I'm gonna, let's say, tell you an introduction about the motion in general. In, let's say, previous year, we talked about the simplest type of motion, which is, let's say, which is linear motion. Actually, this type of motion is the simplest type of motion. We talked about the motion in one, linear motion in 1 dimension, in 2 dimension, and we, let's say, we focused on only on the, let's say, straight line, right? We focused on the motion on the straight line. But actually this year, let's say, which is the last year of your studying actually, this is the last year of high school. You are in grade 12. That's why you read an advanced actually type of motion, which is called rotational motion, or rotational and circular motion together, right? So every type of motion needs, let's say, its quantity. That's why whenever you say rotational motion, so you need to have information about rotational quantity, right? Rotational quantities. Let me read the, let's say, definition for rotational quantity for you. It says, rotational quantities are quantities that are used for what? That are used for describing the angular motion, right? Angular motion of an object. This is called rotational quantity. So quantities that are used for which purpose? For describing the angular motion. What do I mean by angular motion? I'll explain for you. Angular motion means either we have rotational motion or, let's say, circular motion. I'll explain for you. It says, and it consists of, I mentioned it here. It says a rotational, let's say, or a rotational quantity consists of what? Consists of angular displacement and angular speed, right? Angular speed and angular acceleration. So we have 3, let's say, quantities. They are bases of what? They are bases of rotational, let's say, motion. You have to have information about these quantities in order to understand the rotational and circular motion. So you must know what angular displacement is. You should know what angular speed is, and you have to information about angular acceleration. In general, there are 2 types of motion. This diagram. We have this diagram. I'll draw this. Let's say I drew this graph for you. Types of motion. How many types of motion are there in physics? Actually, this is my classification for this chapter especially. Maybe there are some classifications for motion, but I focused on these parts, and I just mentioned two, let's say, types of motion, which are angular motion and linear motion. Actually, this year, I told you in previous year, last year, we talked about linear motion in details, right? That's why this year, let's say, we don't read this subject, linear motion, leave this subject, except for some simple questions in this chapter. We focus on angular motion, right? This is our subject, right? We focus on angular motion. So angular motion itself is divided into two parts: rotational motion and circular motion. Rotational, circular. I want you to distinguish between rotational and circular motion. They are not the same, they are different, right? Let me read the definition for rotational motion. So what's rotational motion? Motion of a body that spins about an axis. Rotational motion, like this Earth globe. We have an Earth globe, actually. This Earth globe, it rotates, yeah? It rotates about its axis. So rotational motion is the motion of object that rotates about itself. It rotates about its axis. This is called rotational motion, right? Or like this one. This, let's say, pinwheel, actually, this pinwheel rotates about, let's say, a pin. A pin here is considered an axis. That's why this, let's say, pinwheel rotates about a particular axis. This motion is called rotational motion, yeah? Rotational motion. Maybe you think about the ceiling fan is another type of rotational motion. Ceiling fan about its axis, right? Like this, for example, let me, if I say it's like a ceiling fan, actually, it can be the motion of the object entirely, thoroughly, is called rotational motion, right? If you take the object, let's say as a whole system, so the motion is called rotational motion. This is the definition of rotational motion, right? Axis of rotation. So what, in order to understand the rotational motion, you have to have information about axis of rotation. So what's axis of rotation? Let me read the definition for you and I'll explain for you. It has two definitions. Actually, in our textbook, it mentions two definitions. Number one, the line about which the rotation occurs. That's the first one. Simply, we can say it's a straight line about which the rotation occurs. Like, for example, Earth globe. There's an imaginary line, imaginary straight line that connects two poles of Earth actually together, and Earth rotates about it, actually. Earth rotates about this axis. This is called axis of rotation. And about the, let's say, pinwheel, actually, about the pinwheel, this pin is the axis of rotation. So it's a straight line that, it's a straight line about which an object rotates. Or I can say, in other words, we can say another definition. It's a line perpendicular to the side of the rotating object or a spinning object. It's a line. This line is perpendicular to the side of the spinning object and passes through the center of the object. Look here. So about this, for example, pinwheel. I told you this pin is axis of rotation. The second definition is more accurate than the first one. The second definition says that it's a straight line that is perpendicular to the sides of the spinning object. It's perpendicular to the surface, or it's perpendicular to the plane of the object and passes through the center. You see, it passes through the center of the object. This is called axis of rotation. or about the Earth globe actually. And I told you there is an imaginary actually axis of rotation that connects two poles together, North Pole and South Pole, and it passes through the center of Earth. This is called actually axis of rotation. So axis of rotation is essential for describing the rotational motion, right? It's very important. Without axis of rotation, you cannot describe the motion of the spinning object, right? So let's move on to another definition or another note. Actually, I wrote two notes for you. Actually, tip number one, I wrote two tips or two notes. Rotational motion. That's the first one. Rotational motion is provided when the axis of rotation lies within an object. So let me underline it for you. Actually, rotational motion. Let me try it with other color. So, yeah, rotational motion. Let me underline it. Is provided when the axis of rotation lies within the object. So, axis of rotation is located inside the object. This motion is called rotational motion. Like what? Like the motion of Earth about itself, like this one. I told you, I showed you the, let's say, Earth globe actually. This is Earth globe. It rotates about itself, right? The motion of the Earth about its axis. This is the first example of rotational motion. The second example of rotational motion of Ferris wheel about itself. This is a Ferris wheel. If you take it as a whole, right? Don't separate the parts. Don't say, teacher, it has a lot of seats and it has a lot of, let's say, lights on the surface of Ferris wheel. Don't care about these parts. Don't separate the, let's say, parts of the Ferris wheel. Just concentrate on the object thoroughly. Just take it entirely, right? So entirely, I can say the motion of the Ferris wheel about itself is the rotational motion. So can I say the axis of rotation lies within the object? That's rotational axis, right? That's axis of rotation located inside the object. Of course, it's located inside the object. It passes through the center of the Ferris wheel. What do you say about this one? So this is the axis of rotation, and I told you it's an imaginary line that passes through the center of the Earth, and it divides the Earth into two parts actually. This is called axis of rotation. So any motion with this property is called rotational motion. Keep in mind that when the position of rotational motion lies within the object, this motion is called rotational motion. That's right. So the position of axis of rotation determines the type of motion, right? Let me repeat the, let's say, note 3. If the axis of rotation lies within the object, so this object has rotational motion. Like what? Like rotating Ferris wheel about itself, or rotating the Earth about its axis, or rotating the pinwheel about its axis, and the axis actually is located within the pinwheel. This is the axis of rotation, and it passes through the center. This is called axis of rotation. And this motion is called actually rotational motion, right? The second tip actually says circular motion is achieved. So there is a new type of motion, right? It's different from rotational motion. I want you to differentiate between rotational and circular motion. The second tip is called, it talks about the circular motion. Circular motion is achieved when the axis of rotation, right, is beyond an object. When the axis of rotation is located outside the object, right? It's located outside of the object, actually, such as the motion of Earth about the sun, motion of Earth about the sun, and motion of a light bulb on a Ferris wheel, like this one, motion of, for example, this light bulb here or here, any point on the Ferris wheel. If you take any point on the Ferris wheel, if you take this seat, for example, if you take this one, focus on one point on a Ferris wheel, whether the point is seat or, I don't know, light bulb, anything. So the motion of this particular point is not rotational, actually, is not rotated, it's circular, right? So circular motion is circular motion. Keep in mind that the axis of rotation is located outside the object, not inside the object, right? Another example, I read it for you. It says motion of a light bulb on a Ferris wheel around the center of the Ferris wheel. So this is called circular motion. So circular motion, I can say, differs from the rotational motion only by one thing, right? Only by, let me compare between these types of motion, right? Here, axis of rotation is located within the object, right? It's located within the object. That's why it's rotational. Here, axis of rotation is located within the object. It's rotational, right? It passes through the center like this. It's perpendicular to the center of the Ferris wheel. That's why Ferris wheel actually, I can say, involves the axis of rotation. But here, axis of rotation of actually this axis is not located within the object itself. The axis here in this situation for circular motion, the axis lies within the sun here. So axis is far away from the Earth itself. That's why axis is beyond the Earth. This type of motion is called circular motion, right? About the Ferris wheel, maybe you said, sir, this is a Ferris wheel and this is a Ferris wheel. How do we distinguish between them? Here, focus on only one point. For example, focus on this light bulb. Study this light bulb in, let's say, several time intervals. Whenever you focus on this, let's say, light bulb, so you want to study the motion of this point, right? You focus on one point on a Ferris wheel, not the entire Ferris wheel, actually. When you focus on this and you observe that this point circles the axis of rotation, it does not rotate. I said circle. It circles the axis of rotation. Why do we say this? Because axis of rotation is located, let's say, axis of rotation actually is far from this point. This is the axis of rotation. That's why, and this is our point. Let me note it as A, for example, point A, and this is the axis of rotation. Axis of rotation is located beyond this point. That's why it's circular motion. It's not rotational motion. But this one, you focus on the entire object. That's why you say Ferris wheel rotates about its axis. Earth rotates about its axis. So we have rotational motion in the case of, let's say, in the case of having rotational, in the case of having axis of rotation within the object. And we have circular motion in the case of having axis, let's say, beyond the object, outside the object. There are examples of circular and rotational motion. Think about, for example, ceiling fan actually. What do you say about the, for example, motion of a ceiling fan, let's say thoroughly? When I take the fan, let's say entirely, what do you say about the motion? Is it, can I say the fan rotates about itself or circles about itself? Think about this situation. Other question, if I focus on only one point on the ceiling actually fan, if I take only one wing or blade, if I say, let's say, determine the motion of the blade of the ceiling fan, blade of a ceiling fan, think about it. I'm not sure whether it's a circular or a rotational motion. Think about it, right? Just focus on the position of axis of rotation. If axis of rotation lies within the object, that's why it's rotational. If axis of rotation lies beyond the object, it's circular motion. I'm sure right now you know the answer, right? Let me reveal the answer for you. So about the entire ceiling fan, we can say it's rotational motion. So ceiling fan rotates about itself. And about each blade, right? About each blade or each point on a ceiling fan, actually, this blade, the one blade of the ceiling fan has circular motion. So we cannot say blade of a ceiling fan rotates. You can say blade of a ceiling fan, blades of a ceiling fan rotate, circle the, let's say, circle the axis of rotation. And let me add one more, let's say, information for you. Let's say rotational motion of Earth provides night and day, actually. It takes 24 hours. So rotational motion of Earth takes 24 hours. It takes one night and day, actually. Circular motion of, let's say, circular motion of Earth provides 1 year. It takes 365.24, let's say, days. So here, about the circular motion, especially about the sun, about the Earth. I'm talking about this Earth, right? It's not true for all objects. You cannot say, teacher, time interval for circular motion is greater than the time interval for circular for rotational motion forever. No, it's not. Let's say it situation is not such this for all cases. Actually, you cannot generalize it. Just for let's say just for Earth, we can say rotational motion takes one night and day. But here, circular motion takes, let's say, 1 year or 365, let's say, days, right? About the, and we have a lot of examples, right? Let me give you another example. Tell me about the type of motion of the moon, right? What do you say about the lunar motion about itself, right? One more question. What do you say about the lunar motion about the Earth, right? So which one is circular, which one is rotational? I'm gonna leave it for you, and I'm sure you know the answer, right? Let me read another question for you, or we wanna move on to another subject. This subject or this title, actually, it's not new subject. Actually, it's new quantity or new expression related to the rotational and circular motion. It's not new subject. It's the new title, actually. Reference line. All of these expressions are essential. They are necessary for understanding the rotational and circular motion. We need these information. So what's the reference line? Let me read the definition for you, and I'll explain for you. The horizontal line from which the angles are measured, right? It's a horizontal line from which the angles are measured and drawn, let's say, to the positive x-axis. So this is reference line. This line, let me determine that this line is reference line, this line. So does it move along the positive x-axis or not? Yes. So this is called reference line. So it's the line actually about which the from which the angles are measured. You can measure the angles by means of reference line. Any angle is measured with respect to this line, for example, angle theta. Whenever you want to measure this angle theta, you have to start from here. So this is a zero level. This is 0 point. This is a starting point. Reference line, it's a straight line. It's a special horizontal line. And keep in mind that reference line means positive x-axis, right? Positive x-axis. It's a, let's say, reference for our motion. It's a reference for example, rotational and circular motion. It's the starting point for measuring the angles, right? And any angle is measured with respect to this axis. If you have a point, for example, if you have a point on the axis of rotation, if you have a point on the reference line, for example, this point has a 0 angle because reference line itself is a 0 level. Any point here has a theta of 0. So angle of these points are 0 because they have no, let's say, motion. They don't have any displacement from this position. They are located on the reference line. That's why, let's say, their motion are considered to be 0. Their angles are considered to be 0. Radius of a circle, or we denote it as r. What's the radius of a circle? It's easy, it's not difficult, but we need these actually expressions for understanding these types of motion. A straight line drawn from the center of a circle to a point on the reference line. So it's a straight line. Radius of a circle is a straight line drawn from where to where? It's drawn from the center. Let me erase the other part. Let's preview. So right now, I'm gonna, let's say, determine the radius for you. For example, for this point, this is our point. Maybe we have a Ferris wheel here. Maybe there's a light bulb, or there's a seat, or there's a participant in this play actually. So this is our point, right? It's a straight line drawn from the center of a circle to the what? To that point. And this point is located on the reference line. This is called actually radius, right? So radius is distance from the center to the particular point. This is called radius. And by the way, radius is measured in meters because it's a distance between two positions. That's why it's measured in meters. In SI, maybe you say, does it measure in centimeter? Does it measure in millimeters? No problem. It's measured in units of distance in general, but in SI, radius is measured in meters only, right? So we have the note here. It says radius of a circle, or R, is measured in, you see, centimeter, millimeter, etc. Maybe you have millimeter and so on, right? But which one is valid in SI especially? This one is valid in SI, right? For example, you have displacement, you have, let's say, radius in centimeter. You have to convert it into the meters. After that, you solve the problem, right? We have other expression, which is arc length. Arc length, or we denote it as S small. What's arc length? Let me read the definition and I'll explain for it. It says, a distance measured along the circumference of a circle. Arc length is a curved path. It's a curved path. It's not a straight line, actually. About the reference line and radius, we said that they are what? They are a straight line. But here, about the arc length is a curved path, yeah? It's a curved path, and measured along the circumference of a circular path, actually. Let me show it to you, actually. Let me show it to you. So this is arc length, right? This is arc length. This is our object, for example. This is rotating object, or let's say spinning object. By the way, if I say spin, look here. Keep it in your mind that spin and rotate, they have the same meaning. If I say, for example, the Earth spins about itself, it's right. If I say Earth rotates about itself, it's true. They have the same meaning. Whether you say spin or rotate, no problem, as you like. They have the same meaning, right? So we have this point on a reference line, and I told the reference line is the starting point, is a 0 level. The object travels an arc length, and I told the arc length is not a straight line. It travels a path along the circular path. Actually, it travels a let's say route along the circle. This is called arc length, and we denote it as S, right? The unit of arc length is meter, centimeter, etc. Right? Centimeter, meter, millimeter. It can be measured in millimeters, no problem. But because there's a distance, right? But which one is valid in SI? Of course, meter is valid in SI. There are, let's say, 3 important expressions: reference line, radius of circle, arc length, and the last one that we needed, and it's very important, angle of rotation. Actually, angle of rotation is very important, especially whenever you want to describe the motion of a spinning object, the motion of the, let's say, of circular motion, right? Angle of rotation, or theta, right? Theta is very important. And by the way, this is theta. So the angle between, for example, the radius and the, between the reference line and radius is called theta. So this angle is located, or I can say the angle that that's located against the arc length, right? It's located against the arc length. Theta is located, let's say, against the arc length. Exactly, that's why this is the position of theta. What does it mean? Theta and S move together. Angle of rotation and arc length move together. Whether this angle actually moves counterclockwise like this, right? Whether the angle moves counterclockwise, arc length moves counterclockwise as well, and vice versa. Whether the angle moves clockwise, arc length moves clockwise also. So they are actually dependent to one another, right? I can say theta and S have to do with one another. They are, let's say, connected to one another. Let me read other information. Angle of rotation. I told you angle of rotation is important. I explained something in advance without reading the definition for you. This is the angle of rotation, right? Let me read the definition. It says an angle through which a spinning object moves. It's an angle through which the spinning object moves. Or angle of rotation, theta, we denote it as theta, is found by the equation. So this is the equation. We have an equation here. This is the first equation of our textbook, actually. This is the first equation for grade 12, the first one. Theta is equal to. So what's this? Maybe this one is a reference line, right? Reference line. And this one is the radius of circular path. This is our subject. it moves, for example, in this direction, counterclockwise. It travels a arc length along a circular path, actually. This is called S, right? S arc length, and this angle is called theta. So theta is measured by two information. What are these information? Actually, theta is equal to theta divided by arc. Theta divided arc length divided by radius of a circle, right? If S actually arc length is measured in meters, right? And radius is measured in meters, so they cancel one another and nothing remains, right? So units counteract one another. In this situation, I can say theta is a unitless. Theta, or angle of rotation, is dimensionless, but I'll explain it for you. Let's say I wrote some notes about the unit of theta, right? We have a note here about the angle of rotation. So this is the equation. I told you this is the first equation of our textbook. Theta is equal to S over R. Circular and rotational motion are described in terms of angles. Actually, whenever you want to describe the motion of, let's say, of angular motion, whether the angular motion is circular or rotational, it doesn't matter. You have to focus on angles, right? You describe the circular motion and rotational motion by means of angles, right? All points on a rigid rotating object, this is another note. All points on a rigid, you see, I say rigid rotating object, except the points on the axis, except for the points on the axis, move through the same angle during any time interval. What does it mean? For example, Earth is a rigid rotating object, right? If Earth is a rigid, yeah, it's a terrestrial actually planet. It's made of actually rock, right? It's not gaseous. That's why it's a rigid object. So this speech or this note is just for a less rigid body. It's not true for gases or liquids. It's just for solid and especially rigid body. For example, we have a rigid body. Whenever you determine any point on the Earth's globe, actually all of these points move with the same angle, except for what? Except for the points that are located at the axis of rotation, right? So we have an exception here. We have an exception. The exception is the angles of is the points of what? The exception is the points located on the let's say located along the axis of rotation of the Earth. Other points actually move with the same angle, right? It says rigid, and I told you actually about the rigid. Why do we say this information is true only for rigid? Because think about, let me give you an example. Think about stars, right? Think about the stars. Stars are not rigid, actually. They are made of plasma. They consist of extremely high gas, right? Extremely high gases. So these gases actually cannot gather in a uniform, let's say, shape, right? That's why the shape is, let's say, changing continuously. In this situation, the center of Earth, right? The center of Earth has a particular angle of rotation that is different from the angle of rotation of the atmosphere of the Earth, atmosphere of the Sun. If I said Earth, I'm sorry about that. Actually, I'm talking about the stars in general. Any star in, let's say, stars in general, and especially Sun, for example, because we belong to Sun, right? Think about the Sun. The center of Sun has a particular angle of rotation. Yeah, right? It's a particular value. But this value for the angle of rotation is different from the axle from the angle of rotation of the atmosphere of the sun, right? So, but what do I mean by this example? I mean that this information, this node, is only true for rigid object. It's not true for. It's neither true for liquids nor for gases, right? But actually, even for the rigid body, we have an exception, and I told you the exception. What are the let's say points that have different let's say angle of rotation with the other parts of the Earth? Only the points that are located on the axis, right? Let me read so I prepared some questions for you, but I'm gonna finish the lecture here. Thank you very much for watching this video, and bye-bye.